Okay, so this question talks about something called jerk. Jerk is a quantity that basically just means the derivative of the acceleration. So derivative of some acceleration, I'm not sure if it's an x or y, but we'll say derivative of some acceleration with respect to time is equal to jerk. Okay, so it's a specific uh, it it's a specific numerical quantity here. So we have a guitar string that's vibrating at a frequency. So let's kind of just highlight everything we have. So we have a frequency at a point in its center, it moves in simple harmonic motion with an amplitude. So we have an amplitude here, right? Amplitude. And then a phase angle of 0. So phi is equal to 0. So we want to write an equation for the position of the center of the string as a function of time. So position means that we're looking for, so A means that we're trying to find some position as a function of time equation, right? And we're looking at it for the center. B, it says, what are the maximum values of the magnitudes of the velocity and acceleration? So we want to find V of t, right? And A of t, and then we want to find Vmax, right? And then A max. Okay, probably shouldn't do capital. I'll keep my cases the same here. Okay, A max. Cool. All right, then I want to find the derivative of acceleration with respect to time, which is the quantity called jerk, and then write an equation for it in the center of the spring as a function of time, and then find the maximum value. So for C, we're going to find this dA, right? dA of t with respect to t value. So this is jerk. And then we want to find max jerk. Okay, so let's start with A. Okay, so the point of this problem with this is going to help us conceptualize. I'll try to clean up my handwriting a little bit here. What this is going to help us like understand is how to take our original equation just for position for as a function of time for simple harmonic motion, and we're going to turn it into literally everything else we need. Okay, so we're going to start with just the general equation for simple harmonic motion, and then we're going to derive everything else from that equation. So we're going to be able to solve for everything just using one starting equation. Okay, so let's do that. Okay, so we're going to start with A. Okay, so for part A, okay, so this is, so x of t is equal to A cosine, right, of wt plus phi. Okay, we know that this is true when we have simple harmonic motion. Okay, so let's kind of look at, let's symbolically solve for all of these and then look at plugging in what we have. Okay, so we also want to find v of t, which is going to be equal to the derivative of x of t, right, with respect to time. So that is going to be equal to, so we're going to do our chain rule, right? So it would be, okay, so be negative a sine of wt and then multiplied by w, right? So negative a sine of wt plus phi, right? Times w, because we're doing chain rule. So we're also going to take the derivative of this inside piece here. So that's going to be equal to negative a w sine. We're just going to move all the constants kind of up front. Wt plus phi. Okay, cool. So we've got that. And then we're also asked to find the acceleration too. So we're going to take the derivative again. So we know that the derivative of velocity with respect to time, right? Sorry, that looks like a partial. This is just a regular derivative, not a, well, it kind of is a partial, I guess. So just derivative of velocity with respect to time. The only thing that's happening here is we just have things changing with respect to time. Everything else is a constant. So let's see. So we're going to take the derivative of this guy that we just did. So what's the derivative of this? Well, with a chain rule again, we're going to have it multiplied by another w, right? And we're still going to keep that negative. So we're going to end up with negative, right? A w cosine of wt, right, plus phi. And then because of the chain rule, like we saw last time, we're multiplying it by the derivative of this interior part, which is going to be multiplied by another w. So taking the derivative of this interior part gives us another w. And then we're going to end up with negative a w squared cosine of wt plus phi. Okay, cool. I'm just checking that there. Yep, that's good. Okay, so now we have the expression for acceleration as a function of time, right? Acceleration as a function of time is equal to this. And then we have our velocity as a function of time is equal to this, right? So this is this for velocity. Acceleration is this. Okay. And then position as a function of time is this guy here. And again, if my handwriting is hard to read at any time, I also posted all of the solutions to this and they are cleaner and typed up. So feel free to follow along with that as well. Okay, so then what are we finding for part C? So we were looking for jerk for part C, right? So we're looking for the derivative of the acceleration with respect to time, right? And that's going to equal this thing called our jerk. Okay, so if we take the derivative of that, we're going to kind of do the same thing again. The derivative of cosine, our negative are actually going to cancel out this time, right? Because we're going to get that negative sign back again. So let's say here, so negative a w squared, right, times negative sine, but for the derivative here, wt plus v, and then multiplied by the derivative of the inside because of the chain rule. So the derivative of the inside again is going to be w, okay? So what's that going to turn into? It's going to be, so the jerk force is going to be equal to a w to the third, right? Cosine of, oh, sorry, a w to the third sine of wt. Okay, and then plus v. Okay, so we got the base equations for everything that we need, right? And then this problem gave us like a lot of stuff that we can plug in, right? What did they give us to plug in? Well, we have the amplitude, right? Which is equal to 3.0 millimeters. Although we do want to convert things to meters. So it would be equal to 3 times 10 to the negative 3 meters. Okay, and then we also are given our phase angle, right? Which is just 0. So we can basically cancel out our phase angle in all of these sections. Then we're given a frequency, and we know W is equal to 2 pi f. So it's equal to 2 pi times, what was our frequency again? 440 hertz. So W is going to be equal to, if we simplify that, it's going to be equal to 2.76 times 10 to the third radians per second. And again, for exams, all of this will be, the math is symbolic. So if you want to practice these problems, I wouldn't really spend too much time like number crunching. I would just make sure that you know how to like symbolically set things up and try to solve for them. I'll give you the final answers here, just kind of plugging in the numbers and point to what we can use. But I won't go really deep into like the nitty gritty of the math. So just A, B, and C. So what we found is that we took this general equation, right, for simple harmonic motion, because we treat it as this like, when we plot our position is like a sine wave, right? So we plot our position as a sine wave because we have an equilibrium point, right? When we're looking at simple harmonic motion, we have some kind of an equilibrium point and we're going back and forth along that equilibrium point, right? If this is our 0, which makes sense when we look at our graph, right? If this is our motion, right, we're going back and forth, and this is our plot with respect to time. Let's say, for example, I'm just going to kind of draw it as a sine curve because I think it's a little easier to look at. But in this case, we actually have a cosine. So actually, I'll do the real one for this problem. So the cosine. Okay, so we're going from A, right, to negative A, which makes sense, right? Because we're like shifting from A to negative A. And if this is our position as a function of time, right, we're getting kind of closer to this center point, right? And then further away, just back and forth over time, right? So if we think about like, if this was like compressed, it would just be like this, right? If we looked at a very small like time step, but it's just sort of that motion is sort of being stretched out over time. So just, I hope those graphs make sense to you guys and why it looks like that. Because they will be kind of important to use for some of the later problems. Okay, so going a little bit into the nitty gritty, but basically I have my A, right? I have my phi, so I can cancel out the phi in each section. I have a value for W, so I can just plug in W. And what this expression wants is just for you to basically plug in and solve for everything. So it'd be like x of t is equal to, then you plug in your a value, right? So plug in the a that I have, right? A cosine of, and I plug in my w, right? W t. Okay, and that would be your solution here. That's what they're looking for this answer. Okay, then what about part B? Same thing. V as a function of t is going to be equal to, and just plugging in the numbers, a times w, right? So this is a negative, and then times w t, and then the plus 0, right? Okay, so you're just going to have some expression as a function of time. So the time variable will still be in there. So yeah, then we'll look at the max right after this. So then I have a of t, and then I plug in this, you know, negative a to times w squared, and then I have cosine, right? Cosine of wt, w times t, right? And then same thing over here, right? I'm just going to plug in what I have. So I'd have a w to the third, right? And then I would have sine of this w and then times t, but then we know that the phi is 0 for all of these, and that would be equal to jerk, right? So then I have an expression for all of these where I'm just plugging in the numbers that I got, that I was given from the problem, and I just sort of simplified a little bit. Okay, so what about this whole business of like the max? What does that mean? Okay, so if I want to find the max, I want to plug in a value basically for the function. So I know that my, so sine of x, right, can be positive or negative 1. Cosine of x can be positive or negative 1, right? That's the maximum value. So what I want to do here, so to find x max, what I'm basically going to do for my x max is plug in, oh, does it ask you for the maximum distance? Position, blah, blah, blah. Oh, they just ask you for the max velocity and acceleration. So I want to know Vmax. So to get Vmax, we're going to plug in, oh, sorry, I took out my sign here. That was a little sloppy. I apologize. Sign. This shouldn't drop out of your equation. This was just an error on my part. Okay. So I want to plug in for my Vmax, it would be negative AW, and then the sine of WT, the max value that I could have for sine of WT that would make this its maximum would be negative 1. So my Vmax would be AW for this. Okay. So then for my acceleration, okay, and then I would just plug in the values that I have for A and W, right? What about for my Amax? Amax. Okay, so this is also negative here. So I would plug in for my Amax, the maximum value I would have is when cosine of WT would be negative. So I would have negative AW squared, right, times negative 1. That would give me my maximum value. So my maximum would be at this AW squared. Okay, so that's the max. Okay, so what about down here? What is my max jerk? My max jerk would be when sine of WT is equal to 1, right? Because that would be the largest magnitude. So jerk max would be equal to AW to the third times 1, okay? And that would be the max. So again, just plugging in the values that you have to solve for this problem. And if you look at the solution sheet, there are some actual numerical numbers there if you want to try to crunch these numbers on your own. Okay, so yeah, so just to summarize, what I set up here for sine of x and cosine of x, this is sine or cosine of kind of any variable in the parentheses. The maximum is like a positive or negative 1 value. And so you would pick whatever value would give you your largest positive magnitude to solve for the maximum velocity and the maximum acceleration, and then also the maximum jerk. Okay, and hopefully this kind of helps point out how we can relate the position as a function of time to velocity as a function of time to acceleration as a function of time to this jerk value.